Here we depict a string of length 40 meters under a tension of 15 newtons, a constant tension of 15 newtons. The mass of the string is 100 grams. We want to predict what the frequency will be in the wavelength for the first harmonic. That's the harmonic, the fundamental harmonic, where the string goes out and back in the middle and stays close to its nodes at the ends. In order to determine the first harmonic, we can see that the wavelength has to be twice the length of the string. If we want the frequency of the first harmonic, well, if we know the wavelength and the velocity of the wave, we can find the frequency. We can find the predicted velocity here by taking the square root of the tension divided by the mass density. Now that is going to be, in this case, a square root of 15 newtons over the mass density, which is mass 100 grams over 40 meters, or 0.0025 kilograms per meter. And when we get done playing with these numbers, we see that the velocity of the pulse ought to be 77 meters per second, which is moving. That's about 150 miles an hour. But you can certainly make pulses move that fast, and you can watch them move. It's an easy way to watch great large velocities. Okay, so for the first harmonic, the wavelength is twice the length of the string. The string is 40 meters long, so that the wavelength is going to be 80 meters. It follows that the period of the wave is going to be the 80 meter length divided by the 77 meter per second velocity. Now this is something we don't want to think about in terms of a formula. We want to make common sense out of this. What has to happen for the wave to complete a period? Well, this whole wave, this whole cycle of the wave, which is 80 meters long, has to pass a point. How long does it take an 80 meter cycle to pass, moving at 77 meters per second? 77 meters, that's what it does in 1 second, doesn't quite get it. It's a little over a second. And it's clear why we have to divide this, and we get the 1.04 second result for the period. The frequency then, of course, is the reciprocal of the period, if you wish, or if we want to think about the frequency, we think about how many of these cycles will pass in a second. Okay? 1 second corresponds to 77 meters. A cycle corresponds to 80 meters, so a little bit less than a cycle will pass in a second. 0.96 cycles in a second to be exact. So that we say that our frequency is 0.96 hertz. We can draw a picture representing our understanding of the relationship between wavelength and period and frequency and so forth. Here's a wave. Crest to crest is the wavelength. If we multiply the velocity by 1 second, well, let's say we get this. Now, multiplying the velocity by second gives us the distance the wave goes in a second. Now, ask yourself the question, how long is it going to take a wave to pass? What's the period of the wave going to be? Is it going to be more than a second or less than a second? Well, the wave only travels this far in a second. It's got to travel this far to complete a cycle. It follows that our period, which is the number of seconds for one cycle, sort of, is equal to the wavelength, the distance that we have to move to complete a cycle, divided by the distance we move in a second, and that the period is therefore lambda over v. That's the kind of reasoning that you ought to understand, because otherwise you're just relying on memorization of a meaningless formula, and the meaning of the formula is much more important than being able to just memorize the formula. Okay. Similarly, with the same picture, to find the frequency of the wave, what's the frequency? It's how many waves pass in a second. Well, here's how far the wave travels in a second. Here's how far we got to travel to complete a cycle. Obviously, less than one cycle is going to occur in a second. Frequency is number of cycles in 1 second, so that's sort of like dividing the distance we travel in a second by the distance we have to travel to complete a wavelength. So the frequency is velocity over wavelength. You should also draw these pictures and make sense of them for where the velocity times a second is much greater than the wavelength. Okay? If the velocity is a lot greater than the wavelength, then we're going to have a lot of waves in a second. And that's a more typical occurrence with a lot of waves that we're going to study, especially with electromagnetic waves later on. Get lots and lots of cycles in a second, because electromagnetic waves, v times a second, is going to be about 300,000 kilometers, okay, close to the distance from here to the moon. Whereas lambda is going to be on the order of a micrometer, a millionth of a meter. So you have a million of these in a meter, and 1 second's worth is from here to the moon. So what's your frequency going to be? It's going to be huge, because you're dividing this huge distance by this very tiny wavelength. So you really need to understand this, and you really need to be able to visualize wavelengths and velocities and so forth. A way to verbally reason this out: the frequency gives us the number of cycles per second. The wavelength gives us the distance per cycle. The distance per second is the number of cycles per second times the distance per cycle. The cycles will divide out, we'll have distance per second. And the distance per second is the velocity of the wave. So what we have here is the velocity of the wave v equals the number of cycles per second, which is a frequency f, times the distance per cycle, which is a wavelength lambda. This is a reasoning out of the basic formula v equals f lambda. If you can reason it out like this, you'll never get it mixed up. You won't ever think it's v equals f over lambda or lambda over f, or in any other way get the thing really confused.